Welcome to the tutorial session on welding. We have discussed the theory part of welding in the last week and in this week in the beginning as well. Welding is of various kinds. It could be gas welding, it could be arc welding majorly. When the arc welding is talked about, we always have electricity supply because arc is always generated because of the voltage difference between the workpiece and the electrode. Then there are certain problem statements that we will try to see what kind of welding we will pick and what kind of the setting of the voltage and current should be there, what is the heat that is generated or dissipated during the welding process. This we will walk through during this lecture. Tutorial session on welding. I am Dr. Amandeep Singh Oberoi from Indian Institute of Technology, Kanpur. Let me go through the concept of the DC welding machine, that is arc length voltage characteristics. Dynamic characteristics of power source. Dynamic characteristics are the rapid transient variation of output current and voltage. It occurs particularly when welding with short circuiting arc starting and arc reignition. To cope with these above conditions, the power source should have good dynamic characteristics to obtain a stable and smooth arc so as the welding is as smooth as possible. Wire feed systems for constant arc length. There are generally two types of feed systems to maintain the arc length: constant speed feed drive system and variable speed feed drive systems. What are these two? Constant speed feed drive systems are having feed rollers that rotate at a fixed speed and are used for pushing or pulling the wire to feed into the weld so as to maintain the arc length during welding. So, this is feed roller that is running at a constant speed and these are drive systems. So, this is my arc that is there. Normally used with constant voltage power source. On the other hand, we have variable speed drive system. In this case, feed roller used for feeding electrode wire are rotating at varying speeds as per the requirement to maintain the arc length during welding. So, it is rotated at varying speed. There is a contact tube. So, depending upon the arc length required, whether the thickness of the workpiece is varying, it is becoming smaller at some point, it is becoming further larger at certain points. So, depending upon the arc requirements, the speed of the rollers monitors the arc length. Variable speed motor is regulated with the help of sensors. Now, arc power is calculated here. Arc power of an arc fluctuates with its length and there is an optimum length for which the arc power is maximum. The optimum arc length L optimum can be determined as follows. We have here V is equal to A plus B into L. So, this V is equal to A plus BL is known as characteristic curve. To explain it further, if I put V is equal to A plus BL, where L is my arc length, consider two cases of arc length L1 and L2 corresponding to arc voltage V1 and V2 respectively. This is something like this. We have the voltage versus current plot V and I, and this is a curve. It is a kind of a quadratic equation curve where I can put two instances. This is one first instance and this is the second instance. I will name this as I1 and here I have V1 correspondingly, and this point is, I will say, P1. Another point P2, corresponding voltage is V2, a corresponding current is I2. So, if L is equal to L1, first case, L is equal to L2, the second case, this is the arc length that is there. This is constant current power supply. I will write it here, constant current. power supply. Here V1 is equal to A plus B L1, V2 is equal to A plus B L2, and current is the function of the arc length, that is I1 is function of L1 and I2 is function of L2. That is there, and if we need to calculate the power that which I showed you, the L optimum, this optimum power if I need to calculate or find, it is something like this here. If I suppose plot my power with respect to length L, so this is how the power curve would look like, and optimal power would be here when it is highest at this point. That means this length is L optimum. Now, if I put here power 1 is equal to V1 into I1 and power 2 is equal to V2 into I2, then at this point if I take derivative of power with respect to L, it should be 0 because the slope on both the direction is coming down. So, that means from this case I could write equating the derivative of power with respect to L, this is equal to 0, I can find L optimum. L optimum. So, about the characteristic curve, there is very interesting finding. There could be constant current curve, there could be even constant voltage curve. It is something like this. I will put it here, this is constant voltage. In the constant voltage curve, with a very small variation in voltage, the current variation is very high, and in the constant current curve, the small variation in current does not lead to very high variation in voltage. I will show you how. I will just redraw this figure, constant current and constant voltage curves, and show you how does it vary. It is something like this. So, it could be two cases, constant current, I am talking about the power source, or it could be constant voltage power source. So, this is something like this. If I plot voltage and current here, constant current curve as you saw in the previous slide, it is something like this. So, if this is suppose the constant voltage curve, it is something like this. Now, suppose if this is the point where we are operating, one point here, one point here. I am naming this point as operating point for constant current, and this is operating point for constant voltage. So, I have current this side and voltage this side, units of current are amperes. Here if I try to plot, see this is a constant current curve, and we suppose there is a variation in voltage. This is voltage where I am suppose working on voltage V1, and this is the variation in the voltage. Corresponding variation in current would be this much only. That is, if this is this difference, if this is delta V, this difference is delta A, change in amperes. This is small. However, in the case of the constant voltage at point OV, if suppose there is small change in voltage, let me first locate the points. This is voltage V2 and current I2. I will name this as current I1. Here the small variation in voltage, you see corresponding current variation is very high. That means this is my delta A and this is my delta V. The arc voltage is directly proportional to length of arc that we have seen here. Consequently, the arc voltage is regulated by altering the arc length. The arc striking voltage has a minimal threshold and open circuit voltage of the power source is evidently greater than this threshold. That is why, that is how, and that is when the welding happens, when the voltage is greater than the minimum threshold, so that the melting and welding does happen. To comprehend the mechanics of arc maintenance, we can have a constant voltage curve or constant current conditions I have mentioned here. The point at which arc voltage intersects with voltage source curve is referred as, so this is the operating point, that is the point where the voltage source intersects with the voltage curve. So this is fluctuating point always. I'm putting here is OC or OV are fluctuating. That means delta V and delta A are the change in the currents. In that case of the constant voltage power source with a fixed V wire feed speed, let me draw another curve here. For example, it is something like this, just to show you how the variation is happening. We have a constant current here, and in this curve itself I draw the constant voltage. Now you know this is constant current CC. I am naming this as constant voltage, I am naming this as CV. Now suppose if there is a point P, I am plotting V and I once again. Corresponding to this point could be represented here. If I say this is my medium arc length and there are fluctuation from here in the current or in the voltage, so these are the corresponding arc lengths. So this is small arc length, this is long arc length. I am talking about arc length. Now with respect to this length, this is the change in the current from here, and also with respect to the smaller length, this is the change in the current. So this is welding current. So in the case of the constant voltage power source with a fixed wire feed speed at point P, a minor reduction in arc length has a slight fall in the arc voltage that leads to comparatively significant rise in the welding current, that is I have shown here. A substantial rise in the current accelerates the melt off rate, thus extending the arc length and thereby restoring the arc voltage to its normal operating level. So this is in the case of the constant voltage power source. In the case of the constant current power source with a steady wire feed speed, a comparable sequence of events occurs, that is the variation in current is significantly reduced, resulting in prolonged duration for the system to achieve self-regulation. The self-regulating system that we are talking about, the fluctuation is there, still there, but system is trying to self-regulate so that the arc length is maintained. In a genuine constant current system, the variation in the current is significantly diminished, so indicating the welder has minimal or no control over the current by adjusting the arc length. So that is why the voltage is more varied whenever we need to control. So this can be corrected by a voltage controlled electrode feed control system. That is, if there is change in voltage, whether rise or fall, the motor accelerates or deaccelerates to maintain a consistent arc length. So we apply here voltage controlled electrode feed system, where the motor accelerate or deaccelerate depending upon the voltage rise or voltage fall. Now, to explain this, let me come to a problem statement, and the problem statement would also help you to understand that how do we calculate, how do we find the characteristic of the curve. A DC welding machine has a linear power source with an open circuit voltage of 80 volts, a short circuit current of 800 amperes. During welding, arc length changes from 5 millimeter to 7 millimeter, and power source current changes from 500 amperes to 460 amperes. What are the arc length voltage characteristics? So, it is telling a linear power source. When I say a linear power source, this means the power source is something like that, a linear line is there. This is voltage, this is current, and here if I say this is my current Is and this is my voltage V naught, it is given that V naught is equal to 80 volt and short circuit current as 800 amperes. Arc length 1 is given, arc length I would say L1 is equal to 5 millimeters, and arc length L2 is equal to 7 millimeters. So, I1 is equal to 500 amperes and it changes to I2, that is equal to 460 amperes. So, this is a straight line. If I say this is 0, from the straight line equation directly I can say V by V naught plus I by Is is equal to 1. This is a straight line equation. This gives me V1 by V naught is 80 plus the current values, that is at 500 and 800 I will put, this is equal to 1. This gives me the value of V1 as 30 volts. This I will call equation 1. Similarly, I can use this equation for V2. V2 by 80 plus 460 by 800, because this is a linear power source. This equation of straight line holds good here. This is equal to 1. This gives me the value of V2 as 34 volt. This is the second equation. Now, we know V is equal to A plus B into L. Therefore, the two equations should give me the lengths. From equation 1, I will write 30 is equal to A plus 5 B. This is at L is equal to 5, and 34 is equal to A plus 7 B. This is from equation 2. This is at L is equal to 7. So, this becomes two equations in two variables. Solving, this is 3 and this is 4. Solving 3 and 4, I get the values of A and B as A is equal to 20 and B is equal to 2. So, now we get the voltage as function of arc length, that is V is equal to A plus B L. So, I can put it as voltage as the function of arc length is V is equal to 20 plus 2 times L. This is the characteristic that is asked in the question, what are the arc length voltage characteristics. So, we got the solution. Similarly, there is a problem statement that asks the optimum arc length and corresponding power when it is given that V is equal to 20 plus 40 L, L is equal to arc length in millimeter. Power curve is a straight line again with the following values: open circuit voltage, that is 80 volts, and short circuit current is 1000 amperes. So, this is a similar problem where we had already been given with the arc length characteristic with this respect to voltage and current. This is again a straight line, as they have said, straight line. Again, I can put it as a straight line here. This is current, this is voltage, this voltage is V naught, this is current short circuit IS, where V naught is given as 80 volts and current is given as 1000 amperes. So, I have to find the L optimum arc length and corresponding power. I have to also find power that is maximum at this length optimum. These two are to be found. Now, we have again seen this is a straight line, again putting the straight line characteristics V by V naught plus I by I s is equal to 1, and putting the values of the given voltage, that is open circuit voltage, and the short circuit current, we can put it here. So, this is a not short circuit, this is open circuit voltage. Okay. We get V by 80 plus I by 1000 is equal to 1. Here I will put it in this way: I by 1000 becomes 1 minus V by 80, and this V, this is A plus B L, which is given here. V is equal to 20 plus 40 L. So, I will put that value here. I by 1000 is equal to 1 minus value of V in the terms of length, that is 20 plus 40 L by 80. To solve this, I get current in the terms of length, that is I is equal to 12.5 into 60 minus 40 L. This becomes my equation 1 here. Now, I know power is equal to voltage into current, very basic electric engineering equation. So, let me put the values here. Power is equal to voltage into current. Voltage is 20 plus 40 L, and I in the terms of L is also given, that is 12.5 into 60 minus 40 L. This becomes a quadratic equation where it gives me 12.5 into 1200 plus 1600 L minus 1600 L square. So, for optimum arc length, we know that dP by dl, that the derivative of power with respect to length, is equal to 0. That is the equation that we saw there. The power optimum is somewhere here. So, here the derivative is 0. Here derivative of P with respect to L should be 0, because we are at the top here. Therefore, putting this derivative equal to 0, this gives me derivative with respect to L. I could say here it gives me 12.5 into 0 plus 1600 minus 2 into 1600 L. This is derivative, this is equal to 0. So, 12.5 is material, this is 0. This gives me 1600 minus 3200 L is equal to 0. L optimum is equal to 0.5 millimeters. Now, this has been gotten. I can simply put this into the equation for the power max in this equation, that is in this equation, to get the value of power that you can calculate. So, we get power, that is the maximum power, is equal to 20 into 10 raised to power 3 watts, that is equal to 20 kilowatts. So, here maximum power at 0.5 millimeters, and with the characteristic of the given voltage, that is V is equal to 20 plus 40 L, we can calculate the maximum power. We can also calculate optimum voltage. V optimum is equal to 20 plus 40 into 0.5, that is equal to 40 volt. Now, we can determine any unknown parameters which are required. Anyway, it was asked to find the maximum power and the optimum length that we have calculated. So, this was a simple problem statement in which electrical engineering voltage, power is equal to V into Y, and a certain state line equations were used. And let us now try to see another problem statement. Here we are using an inert metal gas welding process with the following parameters: welding current 200 ampere, voltage 25 volts, welding speed 18 centimeter per minute, wire diameter as 1.2 millimeter, wire feed rate 4 meters per minute, thermal efficiency as 65%. Determine how much heat is required per unit length, that is to be calculated in kilojoules per centimeter. So, this is simply, as I discussed, a welding bead, something like this. This is filler, upper area, and this lower area is my base metal. I have been given here current I is equal to 200 ampere, voltage as 25 volt, speed, it is welding speed, I will put at V is equal to 18 centimeters per minute, wire diameter D is equal to 1.2 millimeters, wire feed rate, that is Vf is equal to 4 meters per minute, and thermal efficiency is given, that is eta is given as 65%, that is 0.65. Now, we know eta, that is heat input per unit length of weld, that is equal to energy reached per unit energy supplied. That means this is equal to Q into V by energy supplied is electrical energy, that is voltage V into I. This gives me Q is equal to eta times V into I by the speed of the welding. So, this is equal to eta is 0.65, voltage is 25 volts, current is 200 amperes. This divided by the speed, that is 18 by 60, because it is given in per minute, converted into per second. So, this is all in centimeters. So, this Q is equal to 10.83 kilojoules per centimeters. So, next let us talk about resistance welding. In resistance welding we have weld nugget. In the arc welding we had weld bead. So, here heat terms involved in melting efficiency of weld nugget. As we might have discussed in the previous lectures, that weld bead refers to the only visible line that is deposited, and when metal is created and when the welding of two pieces is getting into the action. So, while nugget is specifically localized area and specific in resistance welding, like in spot welding what we do, the joint is heated and melted to form a small localized bond. So, weld bead is a more general term. Weld nugget is specifically when we are talking about the resistance, and I am talking about spot welding here. So, area of weld nugget is pi by 4 d naught minus d I square, that is the outside minus the inside square. Volume of the weld nugget VOL dot, this is area into B. Heat supplied by the power source H is equal to I square RT, that is V by R square into T. Power supplied is equal to VI, that is I square R, that is heat by T. Heat required for welding is HR, that is sensible heat required plus latent heat required. Sensible heat required, that is QS is equal to M into C into the change in temperature. The latent heat required in melting QL is equal to M into LH, that is the latent heat. Heat required to melt the nugget per unit volume HM is equal to Q. Total heat required to melt the entire volume with this would be this heat times the volume, and efficiency would be heat required to melt the total volume of nugget, that is Q into volume, by the heat supplied by the power source, that is I square RT or V by R square into T. Here if melting efficiency is not given, we assume that it is 100%, that is melting efficiency is 100%, that is heat required to melt the volume per unit, the heat supplied by the power source is equal to 1. Heat supplied by the power source is then H, and we have given all these notations already to you. It is I, V, R, T, B, D naught, T, I, area, volume, mass of weld nugget, specific heat of the nugget, change in the temperature, that is the difference between the melting temperature and the ambient temperature, latent heat, the heat required to melt, heat supplied by the power source, and melting efficiency. Let me come to a problem statement. Two sheets of 2 millimeter thickness are spot welded by supplying a welding current of 10,000 amperes for 0.2 second. The contact resistance of 200 micro ohms is created. Heat dissipated to the base metal is 1000 joules. Heat required for melting is 20 joules per millimeter cube. What is the volume of the weld nugget? Volume of the weld nugget, that means we have created with a weld nugget here. So, this inside area is secondary and this outside area is primary weld nugget. It has been asked the volume of the weld nugget when these parameters are given. So, we have been given thickness 2 millimeters, thickness of sheets, welding current I is equal to 10,000 amperes, time is 0.2 seconds. Contact resistance R is 200 micro ohms, that is equal to 200 into 10 raised to power minus 6 ohms. Heat dissipated, that is Q is equal to 1000 joules. Heat required for welding is H, that is equal to 20 joules per millimeters cube. So, given these parameters, I can first start with heat generated. This is equal to I square RT. That means I is 10,000, this square into the R, that is distance, is 200 into 10 to the power minus 6 into 0.2. This is directly calculated as 4000 joules. Heat required for melting, heat required for melting, this is equal to heat generated minus heat loss, which means left hand side heat required for melting, that is given 20 joules per millimeter cube, 20 into volume of nugget is equal to heat generated, that we have calculated as 4000 joules minus heat loss. Heat loss, it is given heat dissipated, that is 1000 joules. I will write it as heat dissipated is equal to 1000 joules. This gives me 20 into volume of nugget is equal to 3000, and the volume of nugget can be calculated here as 3000 by 20, that is 150 millimeter cube. So, this was a simple problem statement, provided we know this relation that heat supplied by power source is I square RT, and we have calculated the volume while using this equation, that is heat required for melting is equal to heat generated minus heat loss. Next problem says to hollow pipe, so 110 millimeter outside diameter and 100 millimeter inside diameter. That means we have been now given the outside and the inside. So, the outside here is 110 millimeters and the inside is 100 millimeters. These are joined by flash butt welding techniques with a power supply of 30 volt. Flash butt welding means it is a resistance welding. At the interface of the joint, 1 millimeter of metal will melt from each end of the pipe, which has a resistance of 42.4 ohms. That is, R is given as 42.4 ohms. And we have given the voltage V as 30 volt. 1 millimeter of metal will melt, that means total thickness, or I will call it width, B is equal to 2 mm, because 1 millimeter of metal will melt from each end of the pipe. Heat required for melting is 60 megajoules per meter cube, that is HM, heat required for melting is 60 megajoules per meter cube. What time is required for welding in seconds, it is asked. So, to find that time, we have to first find the volume of the nugget, and we know heat required is equal to heat supplied using this equation. we will find the time. Volume of the nugget, this is simply pi by 4 d naught square minus di square into the thickness, that is B. This is equal to pi by 4 into 110 square minus 100 square into the thickness, that is 2. This gives me the value of the volume as 3298.67 millimeters cube. This is the volume. Now, heat required is equal to heat supplied. Using this equation, I will just equate to find the value of the time. Heat supplied is I square R T, and heat required is the heat required for melting into the volume. Heat required for melting is 60 into 10 raised to power 6. 10 raised to power 6 is given. 10 raised to power 6 is put because it is megajoules here. This times the volume is 3298.67, it is millimeter cube. To convert this into meter cube, I have to multiply it by 10 raised to power minus 9. So, this is equal to I square, I is V by R. I will put V by R square into RT, because I is equal to V by R, right. So, this gives me 1.97920 into 10 raised to power 2 is equal to this. Putting the value of V and R, I get time T is equal to 9.324 seconds. Another analogy that I would like to touch here in the resistance welding, and well, no more numerical problem I will take. Here we have been given a spot welding setup in which total resistance of the system between electrode consists of following parts, that is R1, R2, R3 and R4. R1 is from the non-consumable electrode and R4 comes down to the weld nugget. So, R1 resistance of the electrode, it is R1. Contact resistance between the electrode and the workpiece is R2. It is at the contact here, R2 is here. Resistance of the workpiece is R3. See, this is electrode, this is our workpiece. Contact resistance between the two workpieces to be welded, that is fairing surfaces, is R4. This is R4 here. In order to acquire a sound weld and to avoid overheating electrodes, R1, R2 and R3 should be kept as low as possible. So, this last problem statement would try to explain me this better. For resistance spot welding of 2 aluminum sheets, each 2 millimeter thick, a current of 5000 ampere was passed for 0.51 seconds. Total resistance was limited to be 75 micro ohms only, and the nugget diameter and thickness were measured to be 5 millimeter and 2.5 millimeter respectively. Nugget dimensions are given here. What would be the proportion of heat energy utilized for welding if the melting energy per unit volume of aluminum welding is taken as 2.9 joules per millimeter cube? Here we have been given the thickness T is equal to 2 millimeters, the current I is equal to 5000 amperes, the time taken is 0.15 seconds. I will take thickness as B because time is taken as T here. Total resistance R is given as 75 micro ohms, that is equal to 75 into 10 raised to power minus 6 ohms. Nugget diameter D and nugget thickness H, these are given as 5 millimeters and 2.5 millimeters respectively. Heat required, I will put it as H, R I will put. Heat required, this is 2.9 joules per millimeter cube. I need to find the proportion of heat energy utilized for welding if melting energy is given as 2.9 joules per millimeter cube. So, volume of the nugget, this is equal to pi by 4 d square h, because nugget dimensions are given, this could be directly calculated. This is equal to pi by 4 into 5 square into 2.5. This is equal to 49.087 millimeters cube. Now, it is asking proportion of the heat energy utilized, that is heat required and heat supplied. Heat required per unit heat supplied with the proportion of electrical energy utilized. So, heat energy that is utilized or electrical energy that is utilized in the terms of heat here would be heat required per unit heat supplied. This is what? Proportion of heat energy utilized. Now, heat supplied, this is equal to I square RT, that is equal to 5000 square into R, that is 75 into 10 to the power minus 6 into T, that is 0.15. This is calculated to be 281.25 joules. Similarly, heat required to form a nugget, heat required is equal to the volume of nugget times the melting energy per unit, This is equal to the volume that we have calculated as 49.087 times the melting energy, that is given as 2.9 joules per millimeter cube. This is calculated to be 142.352 joules. Now, putting these values from equation 2 and 3 in one, putting 2 and 3 in one, I get the proportion of heat energy, that is the melting efficiency, as 142.352 by 281.25. This is equal to around 0.506. That means the efficiency is around 50%. This was majorly some of the problem statements in the welding. So, there are multiple problems that could be discussed in the gas welding as well, which I have not taken in this course, because this is basics of welding. Only very basic calculations I have tried to keep, so that the students from the diploma, students from the first year who are moving to the second year, and students of second year are able to understand these better. And I will now take the virtual laboratory demonstration in the next lecture on welding. Thank you.